So this is the 5-carbon, it's a cation, right? If it's a 4, previously it's a neutral molecule. So in order to have a pi system conjugated, you must have an even number of the carbons in the structures. But that does not mean that odd number of the carbon doesn't make a conjugate system. Odd number of the carbons can make a conjugate system, but every carbon should have a p orbital. Double bonded carbon, yes, they do have a p orbitals, but if these carbons are neutral, that's going to be saturated, that's going to be sp3 hybridized, so no p orbitals available. In order to make it this last carbon conjugated, you have to have the carbon either charged or the being radical, right? Positively charged cation, you have a p orbital possibly available, p orbital available, and then the radical also have an sp2 hybridized, p orbital available. Carbon ion, negative charge also have a p orbital available because they only have a 3 bonds to make. So carbon base will automatically switch to sp2, and then that way you can have a p orbital available, even for the anion. So if you're dealing with an odd number of the carbons in the conjugate system, then you are dealing with the charge system. It's going to either positive charging, negative charging, or it's going to be radical. Drawing the molecular orbital is just kind of same deal. First of all, you throw them the skeleton the same way, and then make the p orbital available every carbon in the skeletons. And then we're going to fill out the bases, the p orbital, to show what the molecular orbital is going to look like. The pi 1 is going to be very simple because the pi 1, anything you talk about, pi 1 is going to be the p orbitals all the way in phases from the C1 to C5. That is going to be the most stable one because it doesn't have any nodes at all. And that's the pi 1 we can easily expect. In a way, that pi 5 is also very simple to predict because that's going to have a node in every bond. But we will do that later. Anyway, the pi 1 is the one that have a no node. So that way, you got the same phases, exact same identical phase in the same phase. But what's going to be the pi 2? To draw the pi 2, we need to place a node, and that's the way the energy goes out. But where are we going to place a node? As I said, we're going to consider symmetry. What the place for the node is basically right in the middle. Right at the middle, there's a carbon there. So they're not going to have they're not going to use their p orbital at all. So that's going to be null. And then the 2 is going to be in phases, and then those going to be in phases, but these 2 are going to be out of phases. So that's a pi 2, looking a bit different. And then pi 3 should have a 2 nodes, right? Where are we going to place the 2 nodes? And that's something we need to think about. And then I guess probably going down there is a more symmetrical than placing any other places. So what is going to be pi 3 look like? We start with the positive bases here, then alternate the negative base there, and then the positive base there. But no 2 nodes can be placed where the carbons are. So that is something that I want to show you. And pi 4 will have a 3 nodes. The worst 3 is going to go, I think the 1 in the right in the middle, and then 2 like this. That way you got the positive phases, negative, and they're going to skip this because these are null. And then now go back to the positive phases and then negative phases. And then pi 5 is basically every bond there's a node there's an alternating positive, negative, positive, negative, positive. And then this system has 5 electrons in the p orbital, comes with the 5 carbons. So we're going to fill out, if you fill out the 5 electrons here, then you are clearly wrong. Because you have to think about, in the pi system, in the neutral molecule, number of double bonds basically what makes those electrons available. But this one's a cation, right? The cation means the p orbital is empty. So in this pi system, it only have 4 electrons. 2 come from there, 2 comes from here, and that one's empty. So we only need to fill out the bottom 2. So that way, same thing. This is going to be the bonding molecular orbital, and that's going to be the anti-bonding molecular orbital. And then what's going to be the middle? That one is going to be non-bonding orbital. Filling this orbital does not increase the stability or decrease the stability. It does not do for the bonding. It does not do anything against the bonding. So this is kind of a non-bonding orbital. If it becomes a radical, that's going to be singly occupied. If it's going to be anion, that's going to be doubly occupied. But occupying this orbital does not do anything to the entire stability of the molecule. So that's why this thing is that the type 3 is considered as a non-bonding.